Okay, guys, welcome to in my study. So today our topic is we are doing chapter two. Okay, chapter two. Let me just focus. Yeah, chapter two, mathematical modeling of physical system. When is gone? Just a second. Okay, now I'm just bringing. Okay, now we have different models and systems in this types of mathematical models, right? First one is differential equation model. And differential equation model, you remember that the differential equation solution is given by CP and and PF, right? Second comes on with transfer function. Now transfer function model, what we have, it is the ratio of Laplace of output. This. What is transfer function? Transfer function is given by this, right? With initial condition equals to 0. Okay. The third one, state space model. In state space model, we there we have optimal control. In this problem is handled more effectively in state space. Oh, that is, if there we have a problem, we are more conveniently and we more easily we can handle the problem. Now we are going to discuss about transfer function, the main topic in this in this lecture. Transfer function, the definition I'm writing. The transfer function of a linear time invariant system, linear time invariant system, that is LTI, linear time invariant system, is depend as the ratio of Laplace transform of output to the Laplace transform of input. We are missing one condition, so the condition is with an assumption that all initial conditions of the system are made 0. This is the condition. This is condition. Now we are dealing with in output and input. in the form of Laplace transform, of course. This is of course, right? Basically, yeah. No, now it's okay. So the formula transfer function is Laplace of output by Laplace of input with initial conditions 0. You should remember this, right? Now let's say review of Laplace transform. Now what we do in transfer function, we have formula how to get into the depth of transfer function, how we deal with transfer function. Let's see. Now if suppose we have a function, we apply transfer function, that means f of t is going to convert in f of s. Transform of function, this is the transform of function f of t. That means function f of t is converted, I just missed out. Yeah, now here this is review of Laplace transform function. Suppose we have f of t, and if we apply transfer function is applied. That means this it is going to convert in capital F of s, right? Transform of function f of t. Now Laplace of a function, yeah. Now the formula, cos, right? Now Laplace of f of t, it is given by, we all know this, 0 to infinity f of t e raised to power minus st into dt. This is the formula of transfer function applied on f of t. Now we are going to see some of the important transfer functions of some some mathematical operators or functions as well. Some important Laplace transform. First one comes with impulse. Impulse function is denoted, we all know, denoted like this: del of t. Del of t is equals to 1 at time equals to 0. I told you in previous lecture as well, equals to 0 when t is not equals to 0, right? Now Laplace of impulse function is equals to 1. You should remember this, which I'm covering in box, right? So second comes with unit step function. We all know unit step function is given by this. Right, I told you in previous class, this is bounded function. This t greater than equals to, this is valid. E of t is equals to 1 for t greater than equals to 0, equals to 0 for t less than 0, and Laplace of u of, that is unit step function, is 1 by s. The third comes on unit ramp function. The graph is given like this: slope Let's take suppose slope is 1, and this is f of t, this is t. Function of function is defined as equals to t at time greater than equals to 0 and equals to 0 for t less than 0. This is the definition of the function of unit ramp function, and the Laplace of unit ramp function is 1 by s square. 1 by s square. Okay. The fourth one comes in parametric function. Parametric function, let's take an example of parametric, like f of t is given by t square upon 2, right? Graph will be something like this, parabolic in nature, and the Laplace of f of t f of t is 1 by s cube, right? This all should you have to remember. Further moving on, we have fifth exponential. Yeah, so yeah, so I'm getting some work. Yeah, we have exponential function, right? Let's say f of t is defined as e raised to power minus 80. For t greater than equals to 0, then Laplace is given by f of t 1 by s plus a. The a is a constant, any constant. The sixth one comes on. Let me do it here. The function is just type of a just a function, a t multiplied by a exponential function. So Laplace is given by 1 by s plus a raised to power whole square, right? These are important formula you should remember. Again, I'm saying, and the second comes on sinusoidal function. In the sinusoidal function, f of t is, we take as sine f of t is equals to sine of t greater than equals to 0. Now the Laplace is given by sine omega t, that is given by s omega upon s square plus omega square. Similarly, if I take here cos of omega t, what I am able to get, there will be s square plus omega square. This is the formula for sine, this is the formula for cos. Now the eighth comes with damped sinusoidal operation, right? Suppose f of t is given by e raised to power minus 80 sine omega t. L of f of t is given by, again, this is omega upon s plus a to the power whole square plus omega square. You should remember. I am again saying you should remember, so that it's good for you. Okay. And now that comes on with 9. No. Let's take, similarly, if cos is there, what will you do? E raised to power minus 80 cos omega t, right? So it will be s plus a upon s plus a raised to power square plus omega square, right? So now some more, because we need to cover all. So let's take sine omega t plus theta. It is given by omega cos of theta plus s sine theta on s square plus omega square. Second, other one comes with s on s plus a is equals to 1 upon a 1 minus e raised to power minus 80. Laplace of 1 minus cos omega t is given by omega square upon s times s square plus omega square. You should, yeah, right. Now we have final value theorem. This is a part of some theorems are there. Final value theorem. In this steady state value for function f of t is determined. How? See this, f of t is there, we apply limit for t tending to infinity, and it is given by limit s tending to 0 s f of s. This is the final value theorem. Sorry, note, I have a note here. Final value theorem है, applicable है if f of s has a no parallels. Did you get what I'm saying? On j omega axis. I told you, if I have not told you, this is j omega axis. Here we have poles like that. So the note is final value theorem applicable if s of f s has no poles on j omega axis. ठीक है जी? Sorry. And now the first is the first one. Second one comes on with initial value theorem, right? Just a second. Yeah, initial value theorem gives just a second gives value of function. What's related? Yeah. Now the initial value theorem, value of function gives value of function at time t equals to 0 plus, and not at time equals to 0, not time less than 0. It only gives at time equals to 0. This is the important condition, the important case I'm telling you here. Limit t tending to 0 f of t, like it will applied only on f of 0 plus. Just remember this. We have limit s tending to infinity s capital F f of s. This is initial value theorem, right? Now note here again, poles on j omega axis is not a constraint. That means poles on j omega axis is not a constraint in the initial value theorem. The poles will be here or not here. It is not a constraint, right? But in as I told you, in the final value theorem, in the final value theorem is applicable if f of s has no poles. There should be no pole on j omega axis. Here it is not necessary. Here it is not a condition. It is not a constraint that always there will be a pole on j omega axis. Okay, done with this. Now let's Laplace transform of some different function. I am telling you of differential function. The differential function, what will be the Laplace or differential function? Like this f of function we have given, it is double differential, right? So we need to find the Laplace. It is easy. S square f of s minus s f of 0 minus f of 0. You should remember this. This is must. This will come in exam. Definitely. Now the second comes with 0 to t f of t dt, right? Now this is f of s upon s plus f of 0 upon s. S will be there, f of s plus f of 0. Obviously in the integration this should exist if f of t exists, right? This will be applicable, then only we will be able to find the Laplace. Now in transfer function we have system. We are getting output if we are giving input. Now how this comes? Yeah. Now we have differential equation for this. Obviously we have differential equation a non t by dtn. Now I'm just proving how the differential, what is how the transfer function comes out, and what is it is it is output by input. So we have differential equation like this: n minus 1 by dt n minus 1 plus goes on a n y equals to b naught dmx dtm plus b1, write it here, plus b1 dx is m minus 1 dt m minus 1. This goes on plus till bmx. This is equation 1, right? What is this? This is differential equation model of the system, right? Yeah, so I'm just taking y of s common, and I'm applying Laplace and taking y of s common from left hand side, and I will be taking x of s from the right hand side after applying Laplace. I told you in previous class, this is equals to that x of y is converted to y of s, y of t, like that f of t is converted to, I have told you that f of t is converted to f of s, all that kind of thing, s of s, right? Here it will be converted like this, and small x of t is converted to s capital X of s. So I am taking x of s common from the right hand side and y of s from the left hand side. Okay, so it will be equals to x of s b naught sm plus b1 sm minus 1. This goes on plus bm. This is equation 2. Okay, now what is transfer function? What is transfer function? Transfer function is equals to output by input. Obviously Laplace. It will be Laplace. So what is that? B naught of Sn plus B1 Sn minus 1 plus this goes on plus Bn upon A naught Sn plus A1 Sn minus 1 plus goes on An. This is equation number 3. This is transfer function. This how this comes from equation 2. I just rearrange the equation 2. I need y of s upon x of s, so I just take and this x of s down and this to other side, RHS. So I get the ratio and put it here. I get the solution. So the highest power. So the highest power of s in the denominator of transfer function is called order of system. Let me write this. The highest power of s in the denominator of transfer function is called order of the system. That is nth order system. Here what is the power of s in the denominator? In the denominator, what is the power of highest power of s? It is s raised to power n. So this is a nth order system. I hope this is clear. Now as I told you, s is a complex variable. S equals to delta plus j omega. This is a complex variable. The transfer function is generally denoted by g of s. This is complex function of complex variable. It's the complex function of complex variable. This is s. This transfer function is generally denoted by capital G of s. So that's all for today, guys. In this lecture, here we have discussed about lot more about transfer function in detail, in depth, and I think this might be clear. So believe. Thank you.